Hello, in this video we're going to talk about a different model to describe covalence bonding known as hybridized orbitals. And so we'll start by talking about hybridized orbitals and what that means, and then later in a different video we'll continue to extend this theory to double and triple bonds. This chapter also contains a description of yet again another way to describe chemical bonding called molecular orbital theory, and that'll be the subject of a future video. So again, different ways to think about bonding. Lewis structure is a very simple theory for molecular structures. It helps explain geometry, which is really nice. It's simple, that makes it applicable and widely used. It doesn't explain why the bonds exist, aside from wanting to make octets. Doesn't explain why there's a difference in bond length between, say, the hydrogen-hydrogen bond and the fluorine-fluorine bond. And so it's pretty limited in what it can do. What it does fairly well, but beyond that it kind of runs out of steam. So now we're going to talk about valence bond theory, where electrons occupy these modified hybrid atomic orbitals which then overlap to form the bond. And then again later comes molecular orbital theory. Okay, so valence bond theory. How do we explain the bonding in, for example, hydrogen? So on the right here we have hydrogen atoms that each one has its own electron in it. That's what this little arrow is that I just drew over. And if the electrons have opposite spins, so one is m sub s plus 1/2, one is m sub s minus 1/2, then as these hydrogen nuclei or atoms come closer, these atomic orbitals will overlap and they form a bonding orbital. And the electrons are now free to roam around this bonding orbital. The overlap of this makes a bond. Kind of a simple, straightforward thing. Just jam these together and it makes a bond. Again, a pretty limited theory, but it works. So this diagram, we wind up showing this kind of logic several different times in the course of learning chemistry. What we're doing here is we have on the x-axis distance of separation, how far apart these two nuclei are. And again, this little diagram up here, the nucleus is up here in the middle of this gray cloud. And so as these nuclei become closer together, as we go to the left here, the energy of this system decreases. It's lower energy to form a bond when a bond is favorable. And so that means the overall energy is lower, and that's what's preferred for molecules. And you get this optimum distance where you have the lowest energy based on some length of your bond. And then if you try to go even smaller than that, well, then you're jamming your positive nuclei too close to each other. And so then that starts to become a higher and higher energy very rapidly. And so this just shows that you have some optimal length right here for your bond. This will depend on your nuclei and the nuclear charge. But at least it gives you an idea of what we're working with here. Some ideal energy that's lower than the two free atoms when you make a bond. So we're showing this with something that approximates s orbitals, but it also works for p orbitals as well. You take your two p orbitals, if they're lined up on the same axis, and here we have the axis connecting the two nuclei. All right, so if you're aligned along this axis and you overlap the two atomic orbitals, you'll make this bonding orbital here. This type of orbital has a name. We call it a sigma orbital. And we'll get into that distinction later when we talk about sigma or pi orbitals in the next video. Okay, so we described this way of making bonds where orbitals overlap to form a bond, and then the electrons are free to roam across this bond. But how do we get that to describe making a molecule? So let's use methane as an example. We know that methane exists as a molecule. This is the natural gas you burn in your stove. How do we describe the bonding here? Well, we know it makes 4 bonds. Carbon generally likes to make 4 bonds. But for the valence bond theory idea here to work, well, you need to have an orbital on your atom that has an unpaired electron in it so that it can overlap with an orbital on the other atom that has an unpaired electron. So that would suggest that only these two orbitals here are capable of forming bonds because they're the only ones with unpaired electrons. So this would say, okay, one atom would come into this orbital, one atom would come into this orbital, and only make 2 bonds. But that's not what happens. Carbon makes 4 bonds. So we have to add something to this. One potential thing we could do is promote an electron. We take the electron from this s orbital and drop it into one of the p orbitals, and that's what we show on the right. Would this work? Now we have 1, 2, 3, 4 orbitals we can use to overlap with other atoms' orbitals to make these bonds, because they have 1 electron in them. Does this work? Well, yeah, you could do this, but you're going to have the wrong geometry. This s orbital is spherical. These p orbitals point along xyz coordinate plane. And we know from the geometry part and from experimental measurements that CH4, methane, is tetrahedral, where the bond angles are 109.5 apart from each other. And if this forms on the coordinate axis xyz, these ones are all going to be 90 degrees apart from each other. So that wouldn't match the geometry that we know to exist in this system. So that's a problem. So one final step is needed to get to a description of how this molecule bonds in valence bond theory, is we have to make what are called hybrid orbitals. And so the definition here is a hybrid orbital is a linear combination of 2 or more orbitals in the same atom that are not already equivalent. So you can't just combine 2 p orbitals together and get a combination that way, but if you combine an s and a p orbital together, then that would work. And in the process of doing this hybridization, these orbitals merge together and form hybrid orbitals. Your overall number of orbitals is conserved. So before hybridization, we've got 1, 2, 3, 4 orbitals. And then afterwards, 1, 2, 3, 4. That didn't change. So what you do is you take the math that describes these s and p orbitals, and you basically add or subtract them together to make linear combinations, it's called. So the math of one orbital minus the math of another one, or you add them together, or things like that. And you'll create these new hybridized orbitals. So again, this comes from mathematics, and we're not going to discuss how that math works, just the outcome of it. So some pictures to visualize this is in CH4, you start with an s orbital and 3 p orbitals, and then once you hybridize, you now have 4 new orbitals that replaced the old orbitals. These orbitals are called sp³ hybrid orbitals because they came from 1s and 3 p orbitals, right? s, 1, 2, 3, sp³. And so over here we have 4 separate orbitals that are called sp³ orbitals. That's the name we give them. Now these hybrid orbitals, they make the geometry work. It turns out they point in the direction of the tetrahedral bonds. So what this picture is trying to show you is the nucleus somewhere in the middle. You have your hybrid orbital that points this direction. It points towards one of the corners of this tetrahedron, which is showing the geometry of the system. And so this just says that these hybrid orbitals point in the directions we need them to in order to make bonds by overlapping with orbitals on, for example, hydrogen. And down at the bottom I have the math showing you just what these hybrid orbitals come from, combining the s and p orbitals in different ways to make these hybrid orbitals. Now finally we can finish off our picture. We take the carbon atom on the left here that has these 4 hybrid orbitals around it, and it may be hard to see, but there's a white hybrid orbital in this drawing right here. Okay, and then when the 4 atoms come to join the carbon with these new hybridized orbitals, again, here's an orbital here that you might not be able to see, and each hydrogen atom is also white in this picture. And so when these go to overlap, they just kind of mush together, and they'll form these overlapping bonds, which then make the molecule happen. Now each bonding orbital that we just made is the same, just with a different orientation. Each one has this sigma symmetry that I alluded to earlier that we'll fully discuss what that means later. And that's basically the picture here. The carbon transitions from its normal s and p orbitals into hybrid orbitals, which costs some energy because you have to promote electrons into these new orbitals that are not as low of energy as the s orbital was in the first place in your carbon atom. but overall that energy is regained by making the chemical bonds. So it costs a little bit of energy, you get a lot more energy back, and it's favorable for forming bonds. Now that we have this picture in mind, let's extend this to other molecules. So ammonia, what do we do with that? Ammonia is tetrahedral electronic geometry because of this lone pair sitting right up here. So we need a home for the 3 hydrogen atoms and that lone pair. The lone pair is going to need to occupy some kind of orbital. So we do the same thing. So on the left here we have our ground state electron configuration of nitrogen. There's 5 valence electrons, 2 of which are in the 2s, 3 of which are in the 2p. And we make these hybrid orbitals on the right, where now there's 4 new hybrid orbitals. They each hold some number of electrons. It turns out that one of these isn't going to be able to bond with another atom to form a chemical bond because there's 2 electrons in here, and you can't make a comfortable overlap if 2 electrons are already in one orbital on the atom. On the other side, these 3 orbitals here are ready to form bonds. They can overlap with, in this case, a hydrogen atom to make the bond because there's only 1 electron in the nitrogen hybrid orbital. Okay, and then the lone pairs hang out in one of these hybrid orbitals, and in this drawing down on the right, here are the lone pairs here, and then the other 3 hybrid orbitals overlap with the hydrogen to make the bond. Here's the hydrogens. All right. Okay, so one conclusion we can pull out of here is that what hybridization the central atom adopts is based on the electronic geometry of that atom. So this hybridization, the sp³ hybridization, was the same hybridization that the CH4 molecule used. It's just now we added an electron right here. That means we have a lone pair on the central atom. If we revert nitrogen back to carbon, if we turn it back into carbon, this electron goes away, and then in this orbital right here, there's only 1 electron, and so then it can overlap with a hydrogen to make another bond. Okay, so when you're doing this, first you have to use the valence shell electron pair repulsion theory to predict the arrangement of these electron pairs, which then you can use to figure out the electronic geometry, which then you can use to describe the hybrid orbitals. So you're going to have to do it in that order. And that's why these problems get merged together a lot with geometry problems, because by the time you've done the geometry and figured that out, it's just one extra little step to determine the hybridization on the central atom. So, as we talked about before with geometry, there's 5 basic geometrical shapes, and then within those there are some sub-shapes. But there's really only 5 shapes for electronic geometry to take on. You have your linear case, you have your trigonal planar case, you have the tetrahedral one, the trigonal bipyramidal one, and the octahedral case. And these have names very similar to sp³, where they consist of the orbitals that these hybrid orbitals were generated from. For example, and we'll talk about this in a minute, this sp² orbital was generated by taking linear combinations of 1 s orbital and 2 p orbitals. And then the ones we just talked about, the sp³, we combined an s orbital and all 3 of the p orbitals to make this nice tetrahedral arrangement of hybrid orbitals. So let's take a tour through this list very quickly here and see how the hybridization looks, see how the electronic energy levels look, and things like that. So say we had beryllium dichloride, which is an octet rule exception. It doesn't need to form octets. So the beryllium only has 2 valence electrons assigned to it in the structure, which is good for it because beryllium only has 2 valence electrons as a free atom, so that works. All right, so beryllium's making just a bond to chlorine on each side, and that's all it does. Okay, so in the free atom, you have electrons in the 2s orbital because there's 2 electrons there, and you don't fill any electrons into the p orbital. So these pictures we're looking at inside this little gray box, you can think of it as a before and after. So this is before hybridization. And then over here, this is after hybridization. Now, the 2 electrons before hybridization are still there afterwards. There's 4 total orbitals before hybridization, so there need to be 4 afterwards. But what these orbitals do is a little different here. So we only need 2 hybrid orbitals because this thing only makes 2 bonds and there's no lone pairs on the central atom. So these two hybrid orbitals, they are called sp because they're merged together from an s and one of the p. So these two orbitals would form, say, the hybrids here. And then these other two empty p orbitals are still present untouched in the atom. Later we'll wind up using these empty p orbitals to make double bonds, but we're not there yet. But don't forget to include them. People have a habit of just forgetting these, and that's bad because you need to include them to show a complete picture of what's going on. So two of the atomic orbitals hybridize, two of them don't. And then in this way, these sp hybrid orbitals can then overlap with the chlorine p orbital that only has one electron in it, and they'll form bonds. And the geometry of this is dictated by what happens when you combine an s and a p orbital together. You get this linear version, which is what we talked about. Each one of these orbitals lies along this axis here, ready to make bonds in a linear direction. All right, next on our list is sp² hybrids. And so our example here is trigonal planar molecules. Say you have Bf3. This is another one that violates the octet rule in that the boron just simply binds to the three fluorines with no lone pairs on the boron itself. So when we hybridize boron, we need to make three hybrid orbitals, each with a single electron in it, so that we can make these bonds to fluorine. And that's really all we need to do. So the before picture is over here with the boron atom, and it has 3 electrons in it, because that's the valence electrons in boron. Notice we're just starting with valence, 2s and 2p. We don't need to worry about the 1s because it's not playing a role here. It's just the valence electrons that are moving around. So we're going to take these 3 orbitals, and we're going to move them into these 3 hybrid orbitals here. These orbitals are called sp² hybrid orbitals because there's an s and 2 p's that make them up. And then you can put the principal quantum number 2 in front of this as well to show that they're 2 sp² orbitals because they come from the 2s and the 2p. So that makes sense. Now don't forget, this p orbital that didn't participate in the hybridization is still around. This p orbital we still need to talk about and say it's still here. So please don't forget to include that. Also, a note about vertical heights here in the diagram we're drawing. So it's a little unspoken, but the vertical axis here is energy. That's what it always is when we draw these electron diagrams. So energy increases along the y-axis. So notice this 2p orbital that's not used, it's at the same vertical height, irrespective of my ability to draw it with a straight line. This is at the same vertical height as it was before. Now these hybrid orbitals, the height they're at is somewhere in between the s and the p. And as long as you park them in between this value for 2s and this value for 2p, as long as you're somewhere in here with your height of your hybrid orbitals, I'm okay with it. So it's showing it's an average of the s and 2p's orbitals, and so its energy level is probably going to be somewhere in the middle of that. A little closer towards the p in this case because there's 2 of them and there's only one s orbital, and that's totally fine. Now the geometry on this works out. So the 3 hybrid orbitals, in this case sp² is here, these yellow things represent the business end of the 3 hybrid orbitals, and hopefully you can see from this diagram they point in the trigonal planar directions here. You know, again, showing some perspective. This one comes out towards you, this one kind of goes away behind you, and here's the one that's in the plane of the page. So they point in the right directions. This p orbital is still here. It's unhybridized. We use it when we make double bonds, so don't forget that it's here. But at the moment we're just going to say it's kind of a leftover thing we're not touching when you make these nice single bonds. And again, down on the bottom, showing how you get the math that describes the hybrid orbitals from the math that describes the various s and p orbitals here. And I already mentioned the geometry, but I'll show you this picture of it again, that you're combining an s orbital and 2 p orbitals to make these hybrids that all point in the directions that you need on the trigonal plane in order to make the bonds 120 degrees apart. Okay, so next up in our tour would be the sp³ orbitals, but we talked about that in our slides a few minutes ago, so I'm not going to continue that discussion here. So next up in our list of hybrid orbitals are the ones that come from an s, 3p, and a d orbital, which we call sp³d, hybrid orbitals. And these orbitals will make trigonal bipyramidal electronic geometries. And an example here is phosphorus pentachloride. So in this molecule, phosphorus has 5 valence electrons, and in the ground state they'd sit in the 3s and then the 3 different 3p orbitals. But as they currently sit, you can't make 5 different bonds because only 3 of these are unpaired. So what will happen here is the orbitals will hybridize and make these sp³d hybrid orbitals. Now you need 5 of them, but the problem is if you count these, there's only 4, and so that's just not going to work. So what happens for these molecules that exceed their octet is that in S, all 3 of the p's, and in this case 1 of the d's, will come together and make the hybrid orbitals. Now don't forget that the unused p orbitals over here are still present, so don't forget to include them. So this reminds us why second row elements can't violate the octets. Second row elements don't have d orbitals because 2d doesn't ever exist. And so you can't exceed the octet if there's no d orbitals because it needs to use one of the d orbitals in order to make the number of hybrid orbitals that are needed to exceed the octet. And the geometry on this again works out. You take the s orbital, 3 of these p orbitals, and then the dz², or one of the d orbitals, I don't need you to know which one, and you make linear combinations of that, and then you get hybrid orbitals that point in the directions that you need to make trigonal bipyramidal bonds. One thing that hopefully hasn't been too confusing, but I recognize might have been, is confusion between 3 and 3. So these are 3p orbitals, of which we're taking 3 of them together. Right, this would also work if you were in n equals 4. You'd take the 4p orbitals and you would still take THREE of them. So hopefully that hasn't been too confusing, the like numbers of orbitals and then the principal quantum number. Okay, finally, if you have an octahedral electronic geometry, then you need to take an s orbital, 3p orbitals, THREE p orbitals, and then 2 of the d orbitals, and you bring these together and you get sp³d² because it came from an s, 1, 2, 3 p orbitals, and 1, 2 d orbitals. And this makes in total 6 hybrid orbitals. And then again you have the empty 3d orbitals that are here that you can't forget about. And these make a geometry that's consistent with the octahedral electronic geometry. Each one of these hybrid orbitals points 90 degrees apart from each other. And so another thing that may have been visually confusing here that I didn't quite go into is if I highlight this, it is one hybrid orbital. So hybrid orbitals have the shape of a main part here, the main lobe we call it, and then a little tiny lobe on the other end. And so they bond this way, and this little tiny lobe on the other end is just present on the other side of the nucleus, which is right here. So when we draw these kind of overlap figures, we'll draw several different hybrid orbitals kind of laid on top of each other. So here would be one hybrid orbital with its little back end on the other side, and then we kind of cover up the little back end to make it look pretty. Again, that's just a nuance, but hopefully that explains some of the diagrams that you've seen in this video. So let me reiterate something here. So if your Lewis structure shows a lone pair on the central atom, then your hybridization energy level diagrams also has to show that same lone pair somewhere in the hybrid orbitals, which are these ones. Another thing that this image shows is that we don't always have to have 3. You know, you can do this with n equals 4, n equals 5, whatever, that matches your central atom. So we'd take, count them 1, 2, 3 of these 4p orbitals, an s, and then 2 of the d, and bring those all together to make these hybrid orbitals here. That arrow needs some help, and that's not it. Okay, so this serves as a good double check. If you have a lone pair on your Lewis structure and don't have a lone pair in your hybrid orbital set, then something is wrong somewhere. They have to match. Conversely, if you have 5 different unpaired electrons, you need to have 5 bonds made to that central atom. So that should match up as well. Some further notes on hybridization. Hybridization is only applicable for atoms that are in covalent molecules and not just isolated atoms by themselves. It costs some energy to hybridize the orbitals, and you get that energy cost back even more so when you make bonds, which is overall lower energy to make these bonds. But without making the bonds, this isn't going to happen. And so only the central atom will hybridize. Now, here's the process. If you want to determine hybridization of a central atom, first you have to draw the Lewis structure, and then you have to determine the electron geometry. What's the arrangement there? Then from that, you can determine the hybridization based on how many electron pairs there are. And you can read this from a table, or you can kind of logic it out. If you have 2 electron pairs, you need places to put them. You're going to get that from an s and a p orbital. That makes 2. If you have 3 electron pairs, you're going to get that from an s and then 2 different p orbitals. That makes 3 total, and so on and so forth. So then recall on this handout I gave, in the far right column it describes the hybridization, and you note these bold lines across the handout is showing that if you have 2 electron groups, you have sp hybridization, 3 electron groups makes sp² hybridization, 4 makes sp3, so on and so forth, right? So even if you've got the T-shaped geometry, it's still sp³d because the hybridization needs to have a place to hold the lone pair electrons, and so they have to be included in that calculus there. Okay, so I'm going to do one example and then we'll end the video. So determine the hybridization of the central atom in water. So the Lewis structure looks a little something like this. Okay, so the electronic geometry of this is tetrahedral. So that means we're going to start with a diagram where energy is increasing on the y-axis, and we'll have the 2s and then the 2p orbitals here. And now in each one of these, there's some electrons. So there's 6 valence electrons in oxygen total. My sad looking arrows here. And so this is kind of our before picture, and then usually what I do is I draw a big fat arrow to the right to say now here's the after picture. And so in the after picture we're going to make 4 places for these electrons to go, and so we need to make 4 hybrid orbitals. And so I'm going to make them vertically between the level of the 2p and the 2s here, right? So we're going to go somewhere in here. And so we'll still put the principal quantum number n equals 2. And then we'll say that these are sp3 hybrid orbitals. The naming here is straightforward, but perhaps a little confusing. These orbitals come from the s and 3 of the p's, but you talk about each individual orbital as an sp3 hybrid. So here's one sp3 hybrid, here's another sp3 hybrid, here's the third, here's the fourth, so on and so forth. Okay, so then our 6 valence electrons are present in these hybrid orbitals. 1, 2, 3, 4, 5, 6. Now, I think we're done, but it's time to do a reality check here and a good double check of our work. So what are we looking for? First of all, conservation of the number of orbitals. We have 4 orbitals on the left and 4 orbitals on the right. That's good. Confirmation of number of electrons. We have 6 electrons on the left, 6 on the right. That's good. Your number of orbitals and your number of electrons aren't going to change. All right. Then we need to check. We've got 2 lone pairs here, and then on our central atom we also have 2 lone pairs, so that's good. That matches, and it needs to match. We also have 2 single electrons in an orbital, in a hybrid orbital, and that matches the 2 bonds that this oxygen will make to hydrogen, so that's good. So that tells us that our structure that we drew is correct and that we're done with the problem. So before we conclude, let me talk about the types of problems that I'll ask you to do relating to hybridization. The first kind is very straightforward. It's just, for a given central atom, what is the hybridization on it? And that comes directly from the electronic geometry, and it's kind of an if-then proposition. If tetrahedral electronic geometry, then sp3 hybridization, so on and so forth. The other kind of problem I'll ask you to do is to draw these energy level diagrams. It'll say, draw the energy level diagrams of the central atom before and after hybridization. And in that case, you have to reproduce the ones that I was drawing here, which involves understanding some of the concepts and what's going on in the hybridization process. Important to know, and something you'll have to learn how to do. Thanks for hanging in there through a pretty long video. And so we'll get lots of practice of this in class. All right, thanks again.